my joshful, energetic students. How are you? So, welcome back to another episode of Noodle Chopstick series. Now, in this series, we talk about two methods that you can use for solving any problem. You can either go with the noodle method, which is all fancy, I would say, and a little complicated, maybe a lot of complications out there, or maybe go a simple method, which is chopstick method. And obviously, this is my choice, but I don't know why many teachers still use it. But see, noodle method is very, very confusing. It is very lengthy, it is error prone, and it is difficult to explain and understand. But still, a lot of teachers use it, and I always think there are two reasons for that. Either the reason might be that when the teachers were the students themselves and they learned it noodle way and they don't even know there's a chopstick way out there, or they did never try to explore it. Or maybe they're aware of the chopstick method, but they want to show that this topic is so difficult that had you not come to me as a teacher, if I'm a teacher, had you not come to me, you would have never understood. See how big of a deal this topic is. It is a rocket science, and you should thank me that I'm teaching you, and whatever. I don't know. I mean, let's not go into that. But we are going to stick to the chopstick method. My name is Bhavdeep, and I've been converting physics haters to physics lovers, and I always say never memorize physics because physics is not supposed to be memorized. It is such a beautiful subject. It's all around you in the nature. With due respect to the textbooks, they are great. I mean, textbooks are great, but I believe that the best textbook out there is nature. Because the problem with textbooks are they're written for a certain curriculum, and most of the curriculum are designed just to teach you things, lot of stuff. Learn this, learn that. But none of the curriculum is designed to make you how to use those concepts. And nature is going to teach you how to use the concepts. Now, today in our series, this episode, we are going to talk about potentiometer. Now, before I start, I would advise you if you have any book, any physics book, open that book, go to this topic, and you see how difficult they have shown this topic to be. This topic starts with a very difficult, complicated circuit diagram. Now, that circuit diagram actually makes students feel scared of this topic. They think, okay, it's a rocket science out here. And some of the students start getting bad dreams about physics because, I mean, it is such a complicated approach to teach this such a simple topic. So, today we are going to go by common sense. We are not going to use any fancy or difficult circuits out there. If that is what you're looking for, you're not at the right place. If you are here for common sense approach, stay tuned. So before I start, let's see what is the challenge. So let's take a battery for example. So let's say you go to the market and you purchase a battery. So what is a battery? Battery has two terminals. There is a potential difference between those two terminals. But what comes as part of an actual battery, a real battery, is also an internal resistance. So there is an internal resistance here, and there is an EMF. EMF is the potential difference between the two plates of the battery. So when you're purchasing a battery, what you get is these two plates, but then you're also getting an internal resistance with it. That's a real battery. An ideal battery would not have it, but we don't live in an ideal world. We live in a real world. So this is part and parcel of this package. So now let's say you bring this battery home and say, okay, I would like to measure how many volts this battery is for. So let's say this battery label says 3 volts, but for whatever reason you would like to measure that. So how would you do that? So it's very simple. You would say, okay, I have a voltmeter in my house. I will use that voltmeter. I'll connect it here. I'll connect it here, and this voltmeter is going to give me the volts. That's the purpose of voltmeter. It is going to tell you how many volts. Fair enough. But does it really do so? Let's think about it. So if this is a voltmeter, in order to measure the voltage, it is going to draw some current. It is going to take some current out of the battery. Now, if you have not seen my previous videos on EMF, internal resistance, please do so now so that you understand this more. But if you have seen them, you know what would now happen is see this voltmeter is this part is connected to this plate. That's good. I mean that's good. This is connected here. But what about this part? This part is not connected here. You have to think about this is not connected here. It is connected here. So what is it giving you? It is giving you not the potential difference between these two. It is telling you between these two. That is the terminal voltage. And how much is that? That is E minus IR. Look at my other videos if you have not done this. So what is happening here is, because this voltmeter is drawing some current, it is going to give you a value lesser than E. If there was no current, then the potential difference here would be E, but then in order to measure, the voltmeter has to draw some current, so it is going to give you lesser reading. So am I saying that this voltmeter is useless? No, I'm not saying that. Voltmeter is very useful device. Look at the simplicity. You just take the prongs here and you connect it and you get the reading. It's very simple. Imagine you have a table and let's say we want to measure the length of it. What you do, you take a measuring tape. You take a measuring tape and you measure it. Let's say it comes out to be 60 centimeters. So the table is 60 centimeters. But then I'm very kind of like perfectionist. I say, no, no, 60 centimeters, you tell me in millimeters. So you'll say, okay, let me measure more carefully. Now it is 60.1 centimeters. So you're going up to the millimeter mark. But then I say, no, 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 tell me up to tenth of a millimeter, thousandth of a millimeter. I mean, is it really worth it? I mean, length of a table, I'm telling you up to a millimeter. Why do you want to go to micrometers now? So beyond a certain level, precision doesn't really matter. And that's what I'm trying to tell here. This battery was 3 volts. Voltmeter has a huge resistance. That means the current is very tiny. If the current is very tiny, this value is close to 3. I mean, it may be 2.94, 2.92, but fair enough. I mean, we get an idea at least. So voltmeters are good to get approximate ideas and very close approximations. But what if for whatever reason I would like to measure the EMFs? Can we say voltmeter can never do so? If you agree with me, give me a thumbs up here in the chat box. Voltmeter can never tell you the EMF. It can tell you a value very close to EMF, but never the EMF. That is my challenge here. So how do we fix it? We fix it using potentiometer. So the resolution to that challenge is you use potentiometer. So why are there two pictures here? This is what we will use in today's class to understand how they work. But this one is very similar to this, structured in a different way. But this is very useful when you turn the volume up and down of your music player. You're actually using that. You're changing the potential divider it is. So you get it in this form. So you should know that you're using it every day. When you have a light, dimming light, right? You turn the knob, the light goes brighter, brighter, dimmer, dimmer. So that's exactly, you are using it. You should know you are using it. But today we are going to use this. So let's see how we use it. So prior to that, let's go for some of the prerequisites. Current flow. What is current flow? We know electrons flow from negative to positive and all that, but we are talking about the conventional current. Conventional current goes from high potential to low potential. So let's say there is a resistor here. If on this resistor, it's part of some circuit that I'm not showing, because the point here is to understand the current flow. Let's say it's part of a bigger circuit, and this point was at 12 volts and this point was at 5 volts. So what would happen? The current would flow this way, because current flows from high to low. But what if this was 15 volts? Now the current goes this way, because the current goes from high to low. But what if, for whatever reason, I mean, there are circuits where this would happen. What if this was 12 and this was 12? Current will not flow. You have seen that in Wheatstone bridge as well. So when the Wheatstone bridge is balanced, so there's no current flow between the middle, the middle resistor, because the potentials are same. So current flows from high potential to low potential. And if the potentials are same, the current will not flow. Yahan jao, yahan jao. It doesn't work. So that's one thing that you should know, and I'm just revising it for you. Secondly is the potential drop. So let's spend some time here. Potential drop. So let us say you have a circuit here. So let's say this is part of a bigger circuit, and this was 3 ohms, and let's say there was 6 ohms. So 3 ohms, 6 ohms. Between them are the conducting wires. So let us imagine that this point is at 0 volts. Let's say, for the sake of understanding. And let's say this one was 18 volts. Now the total available is 18 volts. Now some potential will drop here, some will drop here. this is double than this. It will say I'll take double. And I always take this example. Let's say my favorite fruit, jamun. Let's say there's a big stack of pile of jamuns out there, and there are two kids, and one says I'll take double than you. So what you do is you group the jamuns into three different groups, equal, exactly three, and you give two parts to this person and one part to the other person. That's how you divide into 1:2 ratio. It's very elementary mathematics learned from third and fourth grade onwards. And same thing will happen here. This says I'll take double than you. So total available is 18 volts. You will say I'll make three bundles here. 6, 6, 6. I'll give 6 and 6, 12 to this and 6 to this. So this one should have 6 volts. So if you were to plug in voltmeter here, it would read 6 volts. So that means if this is 0, this one has to be 6 more than that. So this will be 6 volts. Now if you were to connect here, it should give you 12 because 6 and 12. And that's happening here. See, 6 and 18. That's 12. That's how you divide. But now let's say I replace this resistor with a wire. Now this is a resistance wire. It has a resistance. This is not a conducting wire. This is not a copper wire. It's a nichrome wire, let's say. So what is the resistance? Resistance is rho L by A. And now let's say this wire is something, I don't know, maybe um, 10 meters. Let's say 10 meters. So this is 10-meter long wire. So this one is 0 meters, 1 meter, 2 meter, 3 meter, dot, 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 dot. And then this is 9 meter, and this is 10 meters. This is 10-meter long wire, let's say. Now let's say I'm talking about this part. So isn't resistance rho L by A, the rho is same throughout, area of cross section is same throughout, so resistance is proportional to length. So if the entire wire had some resistance, wouldn't this have 3/10 of it? So if the entire resistance was 10 ohms, this would be 3 and this would be 7. If the entire was 100, this would be 30 and this would be 70, isn't it? So whatever is the potential drop across all of this would take 3 parts and this would take 7 parts. Think about that way. So let's put some numbers there. So let's say this one is 0 volts here, and let us say this is 20 volts here. So if I'm talking about this part would should take 3 parts and this one should take 7 parts. So this should take 3 out of 10 parts. So you will make 10 parts of this and say 2, 2, 2, 2, 2, 2, and you will get 3 to this. So you will say, okay, you take 6 volts here. Now think about this. This is getting 6 volts. This is getting 14 volts. And that's how they divide in the ratio of 3:4. So this is another thing that you have to understand, potential drop. So from here to here will be 6 drops of potential difference. From here to here another 14 volts. So now let's find the EMF of the battery. So the challenge we started with today is how to find the potential of the battery. EMF of the battery, not the potential. Now I would again say, if you go by the textbooks, it's such a complicated way. So we'll simplify that. So let us say I have a battery. Let's say I have a battery and I don't know the EMF of it. I would like to know the EMF of it. And let's say there is an internal resistance along with that. It's part of it. Now the challenge was if I plug in a voltmeter draws in its own current and you never get the potential across these plates. You never get EMF, you get the terminal voltage. But now let's say, suppose this was 3 volts batteries, just for sake of understanding, it can be anything. So I'm writing EMF E here, but for sake of understanding, to make things simple, let's say this was 3, and with this was some resistance, 1 ohm, 0.1 ohms. We don't care for now. It's something in the range of 3, let's say. Now let's say I have a wire here. Let's say I have a wire here, and this is a long wire. And let us say it's part of some circuit. There are some more batteries, resistors connected to this, and this is a resistance twinned wire. It's a nichrome wire, let's say, and it's long wire. And let's say this is 0 volts here, maintained 0 volt here, and let's say this is maintained at 10 volts here. Just for the sake of understanding, this is 3 volts of battery, right? So what I'm saying is, let's say I have a wire of 0 volts and 10 volts at one end and the other end. And this obviously, how did this come? As I said, it's part of a bigger circuit, and that part of the bigger circuit is what confuses many students. Primary circuit, secondary circuit. I'm not going into the details to explain for now. In upcoming slides, we'll go through that also. So now let's say I plug in this, and I'll actually change the polarities here. So to make things simpler. So this is this, this is this. So now this is zero, you know, so you can clearly relate. So if this were 3 volts of battery, the smaller one can be thought about as zero, and this one is E. Right. Now let's say I connect these. So let's say I connect it using this wire. So this is zero, this is zero. What if I take another wire here and I have a joystick here? It can move on this, it can slide on it, keeping the contact. So let us say I do that, and what I now do is I have this, and let's say I plug in a galvanometer also in here. So I plug in a galvanometer here, and then I connect it here. Now you can visualize, I mean, this is long, so maybe here somewhere it is 8 volts, 7 volts, because total is 10. So this is 7 volts something, and this was 3. For the sake of understanding, this was 3. So 7 and 3, the current will start to flow here. Remember in the prerequisite, current flows from high potential to low potential. I'm putting it as 7 or 8 here, 3 here. So current flows here. Fine, that's fine. So galvanometer gives me some reading. But what if I connected somewhere here like this? Now this looks to me like 1 volts or 2 volts something, and this was 3 volts. So 3 is higher than 2, so the current will flow the other way. So galvanometer will go the other way now. You're getting the point. So as you're sliding, the current changes because of the potential differences here. So sometimes the current is flowing this way, sometimes this way. But what if you do it somewhere here? And you can visualize this is total of 10, so maybe around 3. So if this was 3, this is 3. Think of it, this is 3, this is 3. No current flows because there is no potential difference. So now you know, let's say galvanometer shows you a zero reading. So this is the part that you have to be extra careful and more attentive. So let's say the reading here comes to 0. So I don't know about this plate as of now. Let's say I don't know about this plate, but I know whatever was here. So let's say this was 3 volts. Let's say this was 3 volts. So I know one thing, if the galvanometer is giving a 0 reading, that means this point is also 3 volts. Ignore the plate here. But all I'm saying is if the current is not flowing here or here, if this were 3, I know the length. I know this is, you know, the 10 parts out there, 3 parts out here. So I know if it is balancing here, as in the galvanometer shows 0, that means this is 3 volts. So then this is also 3 volts. But see what you did just now. Because what you found here is the potential difference between these two terminals. You're still not sure about the EMF maybe, but you know this is 0, this is 3. You know the terminal difference is 3. But since there is no current flowing now, you have balanced everything, so no current is flowing. So don't you think the terminal voltage, which is E minus IR, but now because there is no current, you've balanced everything because this is 0 now. Don't you think what you found just now was the EMF? I mean, I would say if you're watching the recording, pause the video and think about it now. This is mind blowing. What you did, again, the same thing. You found the difference in potential between the two terminals of the battery. But that terminal voltage turns out to be equal to EMF because you now are not drawing any of the current. So mind blowing, I would say, when you have found this. Now, another term associated with this is which we'll use in another slide here is potential gradient. What is potential gradient? Let's say this was some length. So let's say this was total 2 meters of wire. So how much is the potential drop per unit of length? So you'll say 10 volts per 2 meters. So that is 5 volts per meter. Or if you convert to that centimeter, so you can say 10 volts in 200 centimeters. So you would say that is equal to 0.05 volts per centimeter. and that is denoted by letter K. K is the potential drop per unit of length. Because now if you know this and you measure this, you can multiply this by this length. And this was, let's say, whatever length you multiply, you get the potential difference. And that is exactly equal to the EMF of the battery. This is how the potentiometers work. You are able to find the EMF of the battery. But what if you wanted to find the internal resistance? Very easy. Let's go through this exercise one more time. That will give you a revision also. So let's say this was my wire back in action. This was 0 volts and this was some voltage and there were markings on this. And now I have this wire and now I have this battery also. So what I do is I connect this battery here and then I have some internal resistance here and then I plug in galvanometer here and then I do this. I get this reading. Let's call this reading as L1. L1 as in length 1 and this is it's a number line. So I know if this was E, that E is that potential gradient K multiplied by L1. So first thing is what we did is E is equal to K times L1. And this is exactly what we did here actually. So we said, okay, whatever is the potential gradient times this length comes out to be 3 volts and that is exactly 3 volts. Okay, now what if I want to find the internal resistance? Very easy. What you do now is you connect another resistor here, and I'll tell you why. So let's say you connect another resistor, known resistance. You know its resistance, maybe 2 ohms, 5 ohms, whatever. You just connect it. Now think about it. Ignore this part. Do you agree the current will flow here? The current flows here because this is a complete circuit where there is EMF of E and there is a resistance of R and uppercase R. So how much is the current? The current flowing here is E over R plus R. E over R plus R. So what is the potential difference? The terminal difference here is E over R plus R times of R. We have done this in previous videos also. So this is the potential difference here. Now this is not equal to E. This is less than E. See, it's less than the E. So between these 2 points, potential difference is E divided by R plus R multiplied by R less than E. So now this has become lesser. Earlier this was 3, so it was balancing for 3, but now maybe 2.9, 2.8, 2.7, something. So now don't you think it has to balance somewhere here? So this is exactly what you do now. Again, no memorization. What you do now, you have to bring it back to bring it to normal, to zero position. Because if now this was balancing at 3, because of this, it has become 2.9. What will now happen is 3 is bigger than 2.9. So current will start flowing here. So what you do is you bring it here so that it balances somewhere here. And let's call this L2. Now don't you think this portion is balancing this one? So this one is going to be equal to the potential gradient times K L2. So what you found just now is E times of R over R plus R is equal to K times of L2. Very, very easy and common sense way right now. Now, what is your goal? Your goal is to find the internal resistance. EMF you already know. So what you do is you divide these two equations. E crosses out, K crosses out. This jumps up. So what you are getting now is R plus R over R. Oh, uppercase R. I'm really sorry. Over uppercase R. So the uppercase R is equal to L1 by L2. Now this R can multiply there. So let's do that. So in this step itself, I can say, okay, wipe that out times of R. Now very elementary mathematics out there. This R can go there. You factor out R. So your internal resistance comes out to be L1 by L2. Remember, L1 was greater than L2 minus 1. So that this L1 by L2 is greater than 1 times of R. And this is the formula that many students memorize. Or it will come in exam for 2 marks, 3 marks, and they just memorize for shortcut and all that. So you see how easy these things are. All you did is earlier you found without this thingy, you got this length, and that length has to be balancing out E. But then when you put in here, this terminal voltage has to balance the new length. And you eliminate all those variables and you get the internal resistance. So let's practice here. So the question says, figure shows a 200 centimeters potentiometer wire. So it's a 2 meter long wire AB with a resistance of 15 ohms. So this is the resistance of 15 ohms. So they're saying find the balancing length for 3-volt cell, assuming that the cell has internal resistance or no, we don't care, because ultimately when you balance it, this internal resistance plays no part because EMF is same as the terminal voltage. So very easy question. So first of all, let's say this was not part of it. So this is 5 ohms, this is 15 ohms. This battery says I'm going to give you a current of 1 amperes. If it gives 1 amperes, 1 times 15, there's a potential drop of 15 volts here. Another way to look at it is 5 ohms, 15 ohms. This says I'll keep 5 parts. It says I'll keep 15 parts. There are total 20 parts. So this keeps 15 volts. So this here is 15 volts. It is divided by 200 centimeters. So you'll say, how much is K? K is equal to 15 volts divided by 200 centimeters. So this 15 by 200 centimeters. Let's not simplify. Let's keep it this way. They're saying what is the balancing thing? This length has to be equal to 3 volts. So this potential difference has to be 3 volts. So how much is the potential difference here? The potential gradient times this length x. So what we are saying is 15 volts by 200 centimeter times x, that I don't know, I want to find, has to be equal to 3. And this is your answer. So x remains here and 1 by 5, so 40 centimeters. So x comes out to be 40 centimeters. As simple as that. It's so easy. Now sometimes when I'm teaching these concepts, the students are more like, that's all. Yes, yes, that is all. But many students come and say, so and so book was making it very difficult. So maybe you have not taught me the full thing. Students, I have taught you the full thing. It's all about simplifying the things. That's it. Let's do another question here. Very beautiful question here. In a potentiometer experiment, the balancing length is at 240 centimeters with a cell. So there's a potentiometer wire. So potentiometer wire. And they're saying there is a cell here with some internal resistance. And they're saying, okay, there was a galvanometer here. And they say, okay, this was balancing at 240 centimeter. And now they're saying, when you are shunting the cell with a resistance of 2 ohms, as in you shunt as in you put this thing in parallel here. So you say, okay, what if this is 2 ohms here and you do this? So the terminal voltage reduces. Now you have to rebalance out. And they're saying this new rebalance position is 120 centimeters. See how easy it becomes when you draw these diagrams. You read the question, you make the diagrams. They're saying, okay, when the battery was connected, it was balancing at 240 centimeters. When you shunt it with 2 ohms, you get it at 120 centimeter. Find the internal resistance. It's so easy because you have done it common sense way. You remember that. You don't have to memorize, but because it was a common sense approach, we know this. Oh, this is not writing beautifully. So let me try again. So resistance is equal to, uh, remember L1 by L2. So L1 is 240 over L2, which is 120, then minus 1, and all this multiplied by the resistance that you had plugged in over here. So this is 2 minus 1, which is 1 times 2. So 2 ohms. So answer is 2 ohms. And that is how easy these concepts are. Okay, now uses of potentiometer, I was telling you earlier also, it's used as a potential divider kind of when you have a fixed voltage and you want to vary it. So think about it. If you have a fixed voltage here between 0 to 10 and there is a device here and it says I need 3 volts, what you do is you connect it to 3/10 of it. It says 3.1, 3.1, 3.0059. And you can keep varying that. So inside of it, it's a very compact device. It's beautifully crafted and they're very useful. Now again, my students, my point is learning physics is one thing, but applying physics is another thing. So textbooks will teach you a lot of concepts, but unless you apply them, what is the use of it? And you learn a skill. If you're not able to use it, then what's the point? So please keep up the josh and learn the things. Easy method. Share this video, like this video, and put in the comment box what is the next topic that you want to learn from me. And I'll keep coming with more such videos. And I always encourage the students to keep up the high josh. Whatever is your goal, whatever is your dream, your hard work, your passion, and your josh is going to make it possible. So I will see you soon, my dear students. See you. Bye bye.